Have you ever just stopped and wondered what's really going on inside an AI when it looks at a picture and instantly knows that's a cat? It can feel like some kind of dark magic, right? But it's not. It's math. And in this explainer, we're going to pull back the curtain and show you the elegant, surprisingly intuitive mathematics that allows a machine to learn how to see.
I mean, think about it. For us, it's just second nature. We see some fur, a couple of whiskers, those pointy ears, and boom, our brain says cat. But a computer doesn't see any of that. So how do you possibly bridge that gap? How do we take our intuition and translate it into a language that a pile of silicon can actually understand? Well, that's the big question we're going to tackle right now.
All right, so the very first step in this whole journey is all about translation. We have to take a rich, colorful visual image and basically convert it into the only language a computer really gets, the language of numbers. This is where the world of what we see meets the world of linear algebra.
Yeah, this is such a fundamental disconnect. We see a concept, a living thing, a cat. The computer, on the other hand, it just sees a giant grid of numbers. You know, for a simple black and white image, each number might be between 0 for pure black and 255 for pure white. And for a color picture, it's actually 3 of those grids stacked on top of each other, one for red, one for green, and one for blue. The AI's entire job is to somehow find patterns in that massive sea of numbers that always reliably mean cat.
So what do we call this big old container of numbers? We call it a tensor. And please don't let the fancy name scare you off. It's way simpler than it sounds. A 1D tensor, that's just a list of numbers, a vector. A 2D tensor, that's our grid, like a spreadsheet or that grayscale image we just talked about. That's a matrix. And a 3D tensor, well, that's our color picture. It's a cube of numbers with height, width, and those 3 color channels. That's it. The tensor is the basic building block that holds our image so the math can get to work.
So our image is now a tensor, a nice structured block of numbers. The AI can finally get started. It basically shoves this tensor through a whole series of complicated math operations. And what comes out the other end is the model's very first attempt at a guess. But this guess, it isn't clean or easy to understand. Not yet. Let's see how we turn that raw output into something we can actually use.
Yeah, the model's first output is kind of messy. It spits out a list of raw scores, which have a technical name, logits. Now these numbers can be anything: positive, negative, really big, really small. A high score for cat kind of suggests the model thinks it might be a cat, but these scores are definitely not probabilities. They're just this uncalibrated internal mess. We need a way to clean them up.
And the tool for that job is a beautiful little thing called the softmax function. Just think of it like a normalization machine. It takes that messy list of logits and does something really amazing. It doesn't just squash every value so it's between 0 and 1. It also makes sure that they all add up perfectly to 1, or, 100%. This is what turns those raw scores into a real probability distribution, which is exactly what we need to figure out how wrong our guess was.
Let's make this real for a second. Let's say our model spits out these logits: a high score of 3.2 for cat, a lower score of 1.3 for dog, and a tiny 0.1 for car. Okay, now we push these numbers through our softmax function, and look what happens. We get this beautiful, clear probability distribution. The model is now saying, I am 88% confident it's a cat, 12% confident it's a dog, and pretty much 0% confident it's a car. See? Way more useful, right?
Okay, so the model made a guess, 88% cat. That's not bad. But in machine learning, making the guess is just the very beginning. The real learning happens next, and it all starts with a single question: how do you mathematically score that guess?
And this is such a crucial point. So, the model got it right, but it wasn't 100% sure. Is an 88% correct guess better or worse than a 95% correct guess? And by how much? We need a system, a mathematical function, that can give us a single score that tells us exactly how well the model did on this one picture.
And that brings us to what's called the cross-entropy loss function. Honestly, the most intuitive way to think about this is in terms of surprise. If the real answer is cat and the model predicts cat with 99% probability, that's not surprising at all, so you get a very low loss score, a very low error. But what if it predicted dog with 99% probability? Well, that's a huge surprise, right? And for that, the model gets hit with a massive loss score. And that score is the signal it's going to use to learn.
Now, cross-entropy isn't the only game in town. There are other ways to measure error. But cross-entropy, which is that yellow logistic curve you see here, is special. Its power comes from the fact that it's directly tied to information theory. It's mathematically built from the ground up to measure the distance between two probability distributions, what the model predicted and what the truth is. Because of that, it gives a perfectly tuned, meaningful error signal for the kind of guesses our model is making. It's not just a good choice, it's the natural one.
So we have a loss score, a single number that tells us our error. The whole goal of training an AI is to make that number as tiny as possible across thousands and thousands of pictures. And how do we do that? Well, we turn to one of the most powerful tools in all of mathematics, calculus.
In this quote from one of the absolute Bibles of deep learning, it says it all. It's all about optimization. We have a function, our loss function, and we need to find the settings for our model, the millions of little knobs inside it that make the output of that function as low as it can possibly go.
This is honestly the perfect metaphor. Just imagine our loss function is this gigantic, complex landscape full of valleys and hills. Our model's current settings place it somewhere on that landscape, and its loss score is its altitude. To get better, it has to get to the lowest point, the bottom of the deepest valley. The only problem? It's completely foggy, and it can only feel the slope of the ground right under its feet.
So, how does our hiker find its way down? Through a process called gradient descent. First, you calculate your loss. That's your current altitude. Then, using calculus, you find something called the gradient. The gradient is just a fancy word for a vector that points in the direction of the steepest uphill slope. So to go down, you just take a tiny step in the exact opposite direction. Then you do it again. You recalculate, take another step, and you repeat this process thousands, maybe millions of times, slowly but surely walking your way down into the valley of lower and lower error.
Now, gradient descent is super powerful, but it's not perfect. It's got a potential flaw. What happens if the model gets really, really good at the easy pictures, like a super clear textbook photo of a cat? What if it spends all its time and energy trying to get those from 98% correct to 99% correct, while totally ignoring the hard cases, like a cat that's hiding behind a bush?
This is where we can see the real difference between a standard loss function and a more advanced one. Standard cross-entropy is a little bit naive. It gives the exact same weight to every single training picture. It doesn't care if it was an easy win or a tough challenge. Focal loss, though, is designed specifically to fix that problem.
The way focal loss works is actually pretty clever. It just tweaks the standard cross-entropy formula a little bit by adding something called a focusing parameter, or gamma. And here's what it does. When the model is already confident and correct about an easy picture, that gamma parameter basically multiplies the loss by a tiny, tiny number, squashing it almost to zero. It's like it's telling the optimization process, hey, you've already got this one down. Go spend your energy on the pictures you're still getting wrong.
And this graph from the original paper shows it perfectly. That red line is standard cross-entropy. See how it just kind of decreases steadily? Okay, now look at the other colored lines. Those represent focal loss with a higher gamma. As the probability of being correct goes up, their loss values just plummet towards zero way, way faster than the red line. That huge drop is a loss function telling the model, stop worrying about this easy example and move on to something you can actually learn from. It's just a smarter way to learn.
So when you zoom out, what have we really seen? We've gone from a simple grid of pixels to a tensor, from raw, messy scores to clean probabilities using softmax, from a simple guess to a precise error score using cross-entropy, and finally, from an error to an actual improvement using gradient descent. It's not a black box, and it's definitely not magic. It's this beautiful, logical process, an elegant dance of mathematics that allows a machine to literally turn its mistakes into a genuine form of understanding, one tiny step at a time.